Hello students, myself Amrita Dhar, Assistant Professor of Electrical Engineering Department of Greater Kolkata College of Engineering and Management, JIS Group. I will teach you Power System 1.
In this video, I will discuss about evaluation of power system, bulk and micro power grid. Electricity. These topics are included in Module 1 of the subject Power System 1. So, course code is PC-EE-502. Now these topics are newly added in your syllabus. So first, evaluation of power system. The commercial use of electricity began in the late 1870s, where arc lamps are used for lighthouse illumination and street lighting. The history of the evaluation of electric power system is discussed in this video. First, complete electrical system in 1882. The first complete electric power system comprising generator, cable, fuse and load was built by the Thomas Alva Edison, the historic Pearl Street station in the New York City, which began operation in September 1882. This was a DC system consisting of a steam engine driven DC generator supplying power to 59 customers within an area roughly 1.5 km in radius. The load, which consisted entirely of incandescent lamp, was supplied at 110 volt through an underground cable system. Within a few years, similar systems were in operation in most large cities throughout the world. With the development of motors by Frank Sprague in 1884, motor loads were added to such system. This was the beginning of what would develop into one of the largest industry in the world. Next, introduction of AC system in the year 1886. In spite of initial widespread use of DC system, they were almost completely superseded by AC system. By 1886, the limitation of DC system were becoming increasingly apparent. They could deliver power only a short distance from the generators. To keep transmission power losses and voltage drop to acceptable levels, voltage levels had to be high for long distance power transmission. Such high voltage were not acceptable for generation and consumption of power. Therefore, a convenient means for voltage transformation became a necessity. The development of transformer and AC transmission by L. Gollard and J.D. Gibbs of Paris, France led to AC electrical systems. George Westinghouse secured rights to these developments in the United States. In 1886, William Stanley, an associate of Westinghouse, developed and tested a commercial practical transformer and AC distribution system for 150 lamps at Great Barrington. With the development of polyphase system by Nikola Tesla, the AC system became even more attractive. By 1888, Tesla held several patents on AC motor, generator, transformer and transmission system. Westinghouse bought the patents to this early invention and they formed the basis of the present day AC system. Now, AC versus DC, Tesla versus Edison. In the 1890s, there were considerably controversy over whether the electric utility industry should be standardized on DC or AC. There were passionate arguments between Edison, who advocated DC, and Westinghouse, who preferred AC. By the turn of the century, the AC system had won out over the DC system for some specific reason. The first reason, voltage levels can be easily transformed in AC system, thus providing the flexibility for use of different voltages for generation, transmission and consumption. Second, AC generators are much simpler than the DC generator. Third, AC motor are much simpler and cheaper than the DC motor. Now the AC versus DC controversy ended with victory for the AC system. Next, frequency 50 Hz versus 60 Hz. In the early period of AC power transmission, frequency was not standardized. Many different frequencies were in use: 25 Hz, 50 Hz, 60 Hz, 125 Hz and 133 Hz. This posed a problem for interconnection. Eventually 60 Hz was adopted as standard in North America, although many other countries uses 50 Hz. The increased need for transmitting larger amounts of power over longer distance created an incentive to use progressively higher voltage level. In India, we use 50 Hz AC supply because India was under the British government and British government preferred 50 Hz AC supply. Next, early AC system. The early AC system uses 12, 44 and 60 kV RMS line to line. This rose to 165 kV in 1922, 221 watt in 1923, 287 kV in 1935, 330 kV in 1953 and 500 kV in 1965. Hydro-Quebec energized its first 735 kV in 1966 and 765 kV was introduced in the United States in 1969. To avoid the proliferation of an unlimited number of voltage, the industry has standardized voltage level. The standards are 115, 138, 161 and 230 kV for the high voltage HV class and 345, 500 and 765 kV for the extra high voltage class. Next, HVDC transmission system in 1950s. With the development of mercury arc valve in the early 1950s, high voltage DC HVDC transmission system became economical in specific situation. The HVDC transmission is attractive for transmission of large blocks of power over long distances. The crossover point beyond which DC transmission may become a competitive alternative to AC transmission is around 500 km for overhead lines and 50 km for underground or submarine cables. HVDC transmission also provides an asynchronous link between systems where AC interconnection would be impractical because of system stability consideration or because nominal frequency of the system are different. The first modern commercial application of HVDC transmission occurred in 1954 when the Swedish mainland and the island of Gotland were interconnected by a 96 km submarine cable. With the advent of thyristor valve converter, HVDC transmission became even more attractive. The first application of HVDC system using thyristor valve was El River in 1972, a back-to-back scheme providing an asynchronous tie between the power system of Quebec and New Brunswick. With the cost and size of conversion equipment decreasing and its reliability increasing, there has been a steady increase in the use of HVDC transmission. Interconnection of neighboring utilities usually leads to improved system security and economy of operation. Improved security results from the mutual emergencies assistance that the utilities can provide. Improved economy results from the need for less generating reserve capacity on each system. In addition, the interconnection permits the utilities to make economy transfer and thus take advantage of the most economical source of power. This benefits from the beginning and interconnection continue to grow. Almost all the utilities in the United States and Canada are now part of one interconnected system. The result is a very large system of enormous complexity. Next, structure of power system. Now, the structure of the power system can be divided into three parts. First is generation, then transmission, and then distribution. Now, the large network between conductors between the power station, that means generating station, and the consumer is divided into transmission and distribution. Each part can be further subdivided into primary transmission, secondary transmission, primary distribution, and secondary distribution. Now, this figure shows a layout of a typical AC power supply structure by a single line diagram. Now, it may be noted that it is not necessary that all power schemes include all the stages just shown in this figure. For example, in certain power scheme there may be no secondary transmission, and in other case the scheme may be so small that there is only distribution and no transmission. So first we discussed about generating station. Okay, generating station is that part of the electrical power system where electric power is produced by a three-phase alternator operating in parallel. The usual generation voltage is 11 kV. For economy in the transmission of electric power, the generation voltage, that is 11 kV, is stepped up to 132 kV at generating station with the help of a three-phase transformer. Now, it may appear advisable to use highest possible voltage for transmission of electric power to save the conductor material and other advantages. But there is a limit to which this voltage can be used. It is because increase in transmission voltage induce insulation problem as well as cost of the switchgear. The transformer equipped is increased. The transformer equipment is increased, therefore the choice of proper transmission voltage is essentially a question of economics. Generally, the primary transmission is carried out at 110 kV, 132 kV, 222 kV, 440 kV or 765 kV. Next, primary transmission. The electric power at 132 kV is transmitted by three-phase three-wire overhead system to be outskirts of the city. This from the primary transmission, where the power is transmitted at 132 kV by three-phase three-wire system. Now, secondary transmission. The primary transmission line terminates at the receiving substation, which usually lies in the outskirts of the cities. At the receiving station, the voltage is reduced to 33 kV or 66 kV by step-down transformer. From this station, electric power is transmitted 33 kV by three-phase three-wire system at various substation located at the strategic point in the cities. This form the secondary transmission. Next, primary distribution. The secondary transmission line terminates at the substation. Now, where the voltage is reduced from 33 kV to 11 kV or 6.6 kV by three-phase three-wire. The 11 kV lines run along the important roadside of the city. This forms the primary distribution. Now, it may be noted that big consumers having demand of 50 kilowatt are generally supplied at 11 kV for further handling with their own substation. Then secondary distribution. The electric power from primary distribution line 11 kV is delivered to distribution substation. These substations are located near the consumer localities and step down at the voltage 400 volt for 3 phase and 234 for a single phase. This is for commercial uses and this is for domestic uses. Now via 3 phase 4-wire system, the voltage between any two phases is 400 volt and between a phase and neutral is 230 volt. And the single phase residential lighting load is connected between one phase to neutral because the residential load is 230 volt, whereas 3 phase 400 volt motor load is connected across the 3 phase line directly. Now in many worthwhile to mention here that secondary distribution consists of feeder, distributor and service main. No consumer is given direct connection from feeder. Instead, the consumer are connected to the distribution through their service mains. Next is the electrical power grid, bulk power grid. Now, a bulk power grid is an interconnected network for delivering electricity from producer to consumer. It consists of generating station that produces electric power, electrical substation for stepping electrical voltage up for transmission or down for distribution. Second, high voltage transmission lines that carry power from distant source to demand center. Third, distribution lines that connect individual customers. So, a bulk power system is a large interconnected electrical system made up of generation and transmission facilities and their control system. A BPS does not include facilities used in local distribution of electrical energy. If a bulk power system is disrupted, the effects are felt in more than one location. Next is the microgrid. Now microgrid are modern small-scale version of centralized electricity system. They achieve specific local goals such as reliability, carbon emission reduction, diversification of energy sources and cost reduction established by the community being served. Like the bulk power grid, smart grid generate, distribute and regulate the flow of electricity to consumer, but do so locally. Smart microgrid leverage the bulk power system to take advantage of lower cost, baseload power and remote renewable resources. Smart microgrid connect with the larger grid and provide valuable services benefiting both utilities and their customers. They operate in coordination with the utility to improve customer service, but the infrastructure is controlled either in part as with the community or whole as with the university by the local entity. University. Now next question, what are the benefits of smart microgrid approach? The term microgrid reflects a new way of thinking about designing and building smart grid. The microgrid approach focuses on creating a design and plan for local energy delivery that meet exact needs of the constituents being served, whether a city, university, neighborhood, business park or major mixed-use development. At the local level, smart microgrids most efficiently and economically integrated consumer and buildings with electricity distribution and generation. Through smart grid, the economic and environmental benefits to consumer of the smart grid transformation are maximized and are a significant multiple implementation cost.
That's all from today's class. If you have any problem, please contact with me. My contact details is given on the first slide. Thank you.